Now let's get on to Kepler's laws and orbits. So, Kepler's laws are not always something that a lot of people find intuitive. Um, so we'll go over a slower kind of explanation, just because a lot of people, I can understand. I remember I didn't particularly understand Kepler's laws when I first learnt them. Um, but going through them, you do kind of come to understand them a little bit more. All right. So you just need to kind of practice and also remember Kepler's laws in concept don't come up too much on exams. All right. So if you feel like you don't necessarily understand a concept as much, don't worry. A lot of the times on exams, all you need to do for Kepler's laws is just kind of write them out, or maybe solve a problem involving Kepler's third law. But Kepler's third law is just an equation anyway, so it's not too difficult. Alright, well, let's get into it. So, Kepler's laws are related to the orbits of planets. Alright? So, they tell us about how planets orbit other planets. Kepler's first law is that all orbits are elliptical. So, elliptical is kind of like an oval, essentially, kind of like a squashed circle. That's not exactly what it is, but it's essentially what it is. The difference between an elliptical and an oval is that an oval is kind of like a squashed circle, but an ellipsoid specifically is kind of like a squished circle but with two foci. So instead of a circle having one center, it's almost like an ellipsoid has two centers. So, Kepler's second law tells us that a line joining an orbit body to the center of its orbit will sweep out an equal area in equal time. And this is the one that most people have the troubles with. So, we have a line connecting the sun, as you can see, and those two blue areas are actually the same. Those blue areas are equal. But as you can see, the blue area, when the line is closest to the sun, so over here, for this blue area, the planet will travel farther, a greater distance than here. Travels farther here than in here. Right? But these blue areas are still equal because over here it's so far away. So all Kepler's second law really tells us is that a planet will move faster the closer it is to the object it's orbiting. Right? So when this green planet is closer to the sun, it's going to go faster. When it's further away, it's going to go slower. So, a line joining an orbit body to the center of its orbit will sweep out an equal area in equal time. Now, getting on to Kepler's third law, the ratio of the cube of the orbital radius to the square of the orbital period is a constant for a given body being orbited. So, Kepler's third law actually links into an equation. So I'll show you guys over here. This equation allows us to determine the relationship between the radius of orbit, r, the period of the orbit. Remember, period is like how long it takes for one orbit, g, gravitational constant in your formula book, m, the mass of the body being orbited. So in our last example, it would be the mass of the sun. It's not the mass of the planet doing the orbiting, it's the mass of the planet being orbited. And it allows us to find the relationship in between them. And as you might notice, this right-hand side is actually completely constant. G is a constant, M is, it's dependent on the mass, but it's not changing. And then 4 pi are constant. So it tells us that the radius and the period will kind of have a constant ratio depending on the mass. Alright? So let's go over a question here. The Earth takes 1 year to orbit the Sun at a distance of 1 astronomical unit. Alright? Which is 1.5 times 10 to the 8 from the surface. Calculate the mass of the Sun. The radius of the Earth is 6,380 kilometers, and the radius of the Sun is 6.95 times 10 to the 5 kilometers. So, let's go over this. Right? We know that r cubed on t squared equals gm over 4 pi squared. So, we need to calculate the mass of the Sun, which is going to be our big M here. Right? The Earth takes 1 year to orbit the Sun. So we need to put this into standard units. So 1 year is how many seconds? It's going to be 365 days multiplied by 24 hours multiplied by 60 minutes per hour by 60 seconds per hour cubed. Sorry, all the way around. My apologies. So that's the period. On the top, so I'll just leave it. Sorry about this. So this is the period. So we're going to have 365 by 24 by 60 squared, which gives us 3153600. So now the radius, so they are 1.5 times 10 to the 8 kilometers from the surface. Alright, so the radius between them is going to be firstly 1.5 times 10 to the 8 in meters. So we're going to multiply this by 1,000. Now we're going to add half of the radius of each of these planets. So remember, we're going from the center of these planets. That's why we're taking half. So we're going to go plus 6380 times a half times 1,000 because we want it in meters, plus 6.95 times a half times 1,000. Alright, we're going to have 1.5 times 10 to the 8 plus 63 plus 6.95 times 10 to the 5. Sorry. So this gives us an answer of 1.5 times 10 to the 11 as our radius. Now we can go ahead and solve our problem. So we're going to have 1.5 times 10 to the 11 cubed over our period squared, which I'm not going to write out again, multiplied by our gravitational constant, which is 6.67 times 10 to the negative 11 multiplied by m on 4 pi squared. So now let's go ahead and see what answer we get for this. By 6,000 squared multiplied by 4 pi squared divided by 6.67 times 10 to the negative 11. And this gives us an answer of 2.02 times 10 to the 30 kilograms. Right? And that is the mass of the sun. It's a pretty big number, so it sounds about right. Right. Now let's get on to a question where we are recalling that Kepler's third law can be derived from the relationship between Newton's law of universal gravitation and uniform circular motion. So this is something that is important to know as well, and it is explicitly mentioned on your syllabus, as you can see there. So let's start with the force due to gravity is equal to the centripetal force, alright? So we really are linking in the uniform circular motion there, because remember, centripetal force is the force acting toward the center of motion. If we have something orbiting around, there is a centripetal force there because it's moving in a circle, right? So those two forces are equal. Now let's use our Newton's law of universal gravitation on the left-hand side here for Fg, and our formula for centripetal force on the right, which we went through about half an hour ago. So now let's see what we can do here. The first thing is these two m's will cancel out, right? Next, some of our r's will cancel out. We'll get rid of one of these r's over here, all right? So this will leave us with gm on r equals now we were left with v squared on the right hand side over here. So we have the squared here, and we just substituted our formula for v in, so 2 pi r on t, which we went through a little bit ago, and we went to substitute that in. So now, expanding that all out, we are left with Kepler's third law, and that's because, if you have a look over here, we would be left with 4 pi squared r squared on t squared. So we took the t squared over, which is where it came over here. We took the r squared over. The g came over here, and this is where our 4 pi squared came from. Alright, I haven't actually seen that come up in a question before. But I think where you might expect to see it is perhaps on a multiple choice question where it might ask, which of these two concepts can Kepler's third law be derived from? Right? And they might say one of the answers will be Newton's law of universal gravitation and uniform circular motion. And one of them might be, Newton's law of universal gravitation and, Planck's constant in use for the energy of a photon. You know, they'll quote like some other